So next, in the last portion here of 8.4, we are going to be going over the normal distribution of our data and the empirical rule that goes with the normal distribution. So one of the most common distributions that's talked about in statistics is the normal distribution, and this is the one that is mound-shaped or bell-shaped. You can kind of think of it as like the bell curve. It's that typical bell shape of the graph. And this distribution is specifically based on the mean and the standard deviation of the data. And when things line up perfectly and it has that shape, we can say that it is normally distributed for the data. But however, in this class, we are going to be looking at data sets that are already specifically normally distributed and trying to interpret different situations from it using the empirical rule, where the empirical rule tells us that when something is normally distributed, that certain amounts of data is within 1, 2, and 3 standard deviations of the mean of the normal distribution. So to start, our empirical rule tells us that 68% of the data is within 1 standard deviation of the mean. This means that we can take our mean, which in stats we usually use the Greek letter mu here, and we can add the standard deviation to it, add 1 standard deviation to our mean. Or we can also take our mean and subtract the standard deviation from that. And we get these two values here, our mean minus the standard deviation and our mean plus the standard deviation. And between those two values, that is where 86% of the data is within. But then we can continue on. We can take those values and subtract the standard deviation again, and then add the standard deviation to the higher one again. And that is where 95% of the data lies. That's within 2 standard deviations. And then we repeat that process, and we get that 99.7% of the data is within 3 standard deviations of the mean. And now, the very nice thing to go along with this empirical rule is the fact that the normal distribution is symmetric. So this allows us to do some math to be able to get certain percentages of the data within very specific regions of the bell curve. So here on this table, or on this graph that we have here, we have a standard bell curve drawn, and in the middle we have our mean. That's where the mean is always at for a normal distribution. And then we have subtracting the standard deviation with the Greek letter sigma going to the left and adding the standard deviation going to the right for this. So looking at here, we have that 68% of the data is within 1 standard deviation. So that's between this dotted line and this dotted line here. But since our normal distribution is symmetric, we can take that 68%, break it in half, and we get that 34% is on this left side here, and 34% is on this right side here, in those very specific regions of our normal distribution. But then we can continue on that process because we know that 95% of the data is within 2 standard deviations. So that gives us between this region and this region of our graph, we know that 95% of the data is in there. So we can do a little bit of math, break that in half. So 95 divided by 2 is 47.5. That's, however, covering this entire region on the left side, from the mean to the mean minus 2 standard deviations. But we already know that 34% of that is in that section that I highlighted in red. So if we take away 34 from our 47.5, that gives us this 13.5 in this one particular section of our normal distribution. And we have the same thing happen on the right side over there between mean plus 1 and mean plus 2 standard deviations. And then once again, we can repeat that process because our empirical rule tells us that 99.7% of the data is within 3 standard deviations. So we can divide that in half, subtract that 47.5 that we know is already allocated to that specific spot, and that gives us that 2.35% is in both of these two little small sections here on the end. And then lastly, what's not written here is the spot after the plus 3 standard deviations and the minus 3 standard deviations. And there's actually 0.15% in those very tiny sections under the curve that we can't really see because to our eyes, it looks like it's basically touching the x-axis at that point, but it's technically not. There is a very small amount, very small percentage, the 0.15, that is underneath that section of the curve.